off.
I just wanted to make sure that the recording was gonna go work properly.
Okay. I did not prepare for this this.
It and honestly, like there's a lot of other papers as well that's going on. You don't have to take up the full time. It's there's always people that are interested in other things.
Is there which other papers are people interested in?
I mean, just like stuff that was dropped in the channel.
Okay, we are streaming. Let me try.
It's useful to mute. There's a button on the top bottom right to mute all or um, yeah, mute people on entry so that can help because people don't realize they're unmuted.
Settings. Okay, where's the mute all on entry? Can't seem to find that CD button either.
Bottom right, there's like a little drop down.
But okay, yeah, found it. Mute participant on entry. Got it. RJ, were you saying something? Because I can't hear you at all.
Sorry, I was not muted. No, I wasn't saying anything.
Okay.
I'm at a cafe, so there's a lot of background.
Got it. Okay, I guess I'll go through RADLAD and I'll go through large language diffusion model. Since I don't know whether you all saw the tweets from recently as well, because apparently Google now just made a decent diffusion model, text model, which is quite rare. So AI is apparently going to get much faster today. Okay. Okay, anyone? Okay, so so today's going to be like a collection of papers. I will kick off with my own, which is RADLADS, and then where we show how to essentially take an existing 72B Quen model and convert it to another architecture altogether. And then after that, I will go through the diffusion model, I guess paper, and then we'll like pick up from any other suggestions from there. So the paper that we are covering, I'm just going to put the link here and share my screen. Got it. Yep. So so I think a few of you may have already heard about me mentioning this in overall. But this was essentially the basis for our quirky 72B, which is where we took an existing Quen 72B model. Let me find the title one, which is better. Yeah. Where we took an existing 72B model and essentially were able to train it using a new attention mechanism, and we were able to get most of the performance retained. The subsequent paper that we published is more of like to document that process from a high level, and then subsequently also what we found didn't work in particular. So the idea here is that we want to actually encourage and research into new attention mechanism. And this technique doesn't apply just to RWKB. This approach actually unlocks new possibilities for not just RWKB, but that includes state space model, XLSTM, and etc. And essentially, what we realize is that majority of the feed-forward network layer can be recycled. If you there is actually a similar paper that came out recently as well. MLPs similar across architectures. I can't remember the exact name. I didn't. But basically, there was a recent paper that came out where a team compared the Llama model and the Mistral model, and I believe one more model, and they found that actually that the the MLP layers weight values are approximately similar to each other, despite being trained on different data sets. When they are of similar size. So there's kind of like hypothesis right now floating around that if you're going to train on the same large web data, your MLP layers are going to converge to roughly the same. And we also like reaffirm that hypothesis that hey, you can freeze that layer and just swap out the attention layer. So what we did subsequently, and so really is that we showed like this is not the first conversion method per se from an existing from one architecture to another. So we did outline it, the comparison to like to compare to existing methods, acknowledging some of the previous work that was done accordingly. But I think what stood out for us is that we are probably one of the first team that went, after going through this process and only training on 500 million tokens, that we actually even have benchmarks improve, and even though some actually did improve. And like previously, right? Previous conversion attempts, right? You will see a dramatic drop in performance, which is not really the biggest issue in my opinion, because like when you convert from a quadratic to a linear model, even if let's say you drop by 20% performance in overall, the inference saving is actually substantial enough that uh that that this could potentially be a viable path towards like making a more scalable model. But with the updated techniques that we did with RADLADS, right, it's that it's able to like more like rapidly forgot to talk about it. Itself rapid attention distillation to linear attention decoder. So we are able to rapidly change one attention mechanism to another. The linear one is just because of the example, because we are a linear architecture. But like I said, this can be done using other attention mechanisms. Like right now, we are actually helping two universities, and we are talking to another two and their team to test and variation of the transformer attention model using this same technique. So what we did was that we take the existing model, we freeze the feed forward network layer, and we we swap out the attention layer, and then subsequently, right, we distill the information in between. I know a lot of people get confused about the distillation since I conveyed the idea, and it was covered in this paper, is that when we say distillation, right, we mean distillation from the same model, from the original model, and it's not just logic distillation. Like the first few steps of the process, right, is that we distill it in between the layers. So for example, you can take a single block, you put the you as you do the forward inference, and as it goes through respectively, right? We take the incoming embedding and the outgoing embedding, and we use that for distillation, not the logics itself. So yeah, distillation between the layers itself, because in this case we are replacing the attention mechanism. um and then subsequently, you fine tune that, you do further fine tuning to like just stabilize and weave everything together. So I think since we released this paper, right, background, I covered the high level there. What actually a lot of people pointed out and really liked about it. So after the logic distillation experiments and benchmark, I wanted to highlight this segment. What did not work? Because the thing is like with this conversion method, right? There's many ways you can get it wrong, and these are some things that uh we 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 actually iterated through, and so we documented like what did not work. We also would like to clarify that when we say it did not work, and we mean very specifically did not work for RWKV. It is possible that as we experiment with other attention mechanism, right, that some of the things that we flagged out as did not work will work with other attention mechanism. So even though we listed it out here, right, we are already like breaking the rules for one of the experiments that we are already doing. So um, so like for example, one of the things that did not work, for example, which we thought would, is that so when we took so one of the shortcuts that we tried to do, for example, is that we took the existing attention module weights and copy it over to RWKV. Because at the end of the day, RWKV is still matrix multiplication. The weights can be copied over, and we just like maybe it'll work, did not work, respectively. It was better
So
to start from.
client commented on their his leadership skills. So we made a pushback on their decision today. So we will hear most probably tomorrow how the direction will go. If that is not the case, we are asking to consider him for a different role in Relax. So
Sorry, yeah, that didn't sound like a question, right? Yeah. So yeah, we then subsequently yeah, like I said, so we ablated this and then we tested it like from starting the attention mechanism from scratch, pretty much same score. So we end up skipping that. Even though I mentioned freezing model weights, right? You I think one of the things to point out is that you want to freeze only at stage one. So it goes through several stages. The first stage is you replace the attention layer, and then you do a quick chain. And then subsequently you will want to unfreeze the MLP layers. The reason why we found that this was needed is that especially over longer context length, right? The performance will drop otherwise. Things like that. Batch sizing is extremely tricky, but I think this is the case for actually any large model, but it's just particularly so within this process. And to be clear also, like, and this is actually further confirmed with one of the upcoming reasoning models that we did, right, was that you will need to have the data set that's reflective of the data that is in the model. So for example, we recently did one of the reasoning model, we converted it. uh, Spoiler, is the latest Quen 3 model, and we didn't release it because when we did the conversion, we didn't convert with the reasoning data set. So when he tried to do the reasoning token and things like that, it just went crazy. um, we are now redoing the process with reasoning tokens, and subsequently this will be we believe this will perform much better. So like your data set should be approximately the same of what's your original model data set, which is a challenge because we have absolutely no idea what is Quen data set. So so that's one thing to take note. Another thing that we tried, for example, is like we tried to do LoRa based for the conversion process. It just made things a lot worse. Yeah. So the reason why we decided to document all the what did not work is that like once again, there is a lot of benefits for this mechanism here, this approach, right? For new attention mechanism, not just RWKV, and we just wanted to like outline like some of the key things there. So yep, and so for those who don't know what RWKV is, and I think most people in this group already know, is that it's a linear attention mechanism that my group has been building and scaling up. So with this, right, we have now built the world's largest 72B model that doesn't have the transformer attention mechanism. The benefit of it is scale linearly over 1000x cheaper inference cost, yada yada. And but what I find more exciting about us covering this paper itself, right? This paper is that it's not really so much about my architecture, because I'm also on record saying that I don't think our architecture is final, and and that and that there's so much more improvement to be made. So if anything, right, I actually do think there needs to be more research into other ways to build AI architectures, because like one of the things that I said at ICRR, where I presented the earlier version of this, is that was that right now the largest models to date, right, are not reliable enough to do cashier duty or day-to-day work tasks. And we are basic and well, scaling does help it, right? If we scale 7 times more, because the scaling law is like you scale 10x to get 10% improvement, that will be the entire energy of the earth required to train the model. So at some point, right, we do need a better attention mechanism to lower the energy cost, or to like just make things more reliable, or to make things a scale better. And previously, most of the existing labs avoid doing this because to validate any new architecture, you will need to, and this is from our experience, you need to iterate around 20 to 80 times before you can find an architecture that has a 10% improvement. You're going to get more failures than success. And when each try can cost up to $5 million in that training process, yeah, we are looking at tens of millions of dollars to try experiment on new architecture, and that 10 million could be just to train more tokens. But this changes things. If it's now 2,000 to 20,000 to test a new attention mechanism, it unlocks the door to literally anyone who is willing to spin up a run pod instance, for example. And that's how that and that's why we expect more experiments to do so, and which links very well to the most very recent thing about Gemini diffusion model. I think I also said that diffusion models are probably interesting because of two things that I want to find out. Like one is that diffusion models, at least for images, have been highly resistant to catastrophic no sorry to overfitting, in the sense that, like, you may have heard like of large language models overfitting after they see the data 3-4 times, for example, or even 2 times, and they start going like crazy or inferior. Diffusion models, especially in the image space, are typically trained over 1,000 times with the same data, and they did not go crazy. And I've been saying that I want to see more success in text diffusion model, because I want to actually find out and test the hypothesis about why does diffusion models become more resilient. And this is well, this is not open source. Google Gemini has recently released a diffusion model as they demo that is blazingly fast. So linking that, right, is that there's on the open source side, right? So that is proof that diffusion model can actually work as potentially even replacements to my architecture and transformer architecture. This is the paper covering large language diffusion models, and so this is the team that trained the LADA AB, which then which is then to be used and then they benchmark it across the spectrum of tasks. So I think what is interesting for diffusion models is that for this in particular, right, what is I think the easiest way to view a text diffusion model is that instead of pixels on the screen, you you replace that with actually just the byte values, and that essentially means that that same process, right, of how you like you generate an image, and then it slowly updates the values, right. I think I'm just going to show this as a demo example. As you can see, it slowly updates like word, token by token, character by character, and the downside for this is that you won't get that streaming token effect, and respectively, and your time to first token, air quote there, might be much longer. The benefit for diffusion model is that if let's say you're generating 1,000 tokens, you might be able to generate all 1,000 tokens in, let's say, 100 steps, which means it's faster in overall. Yeah. I think what is interesting about this as well, right? This paper in particular, is that like as the way they said it, right, is that one is that the model itself, right, for diffusion models, which, to be clear, this is too early to say. In my opinion, 8B is too early to even draw conclusions, right, was able to outperform Llama, right, in context learning and reversal reasoning. Reversal reasoning is the issue when, let's say, like A is related to B, B is related to C, and you have like a statement like that. Is the model able to deduce logically that C is equal is related to A in a single hop? This is partially mitigated now with the chain of thought reasoning or deep thinking or whatever you want to call it, or one style reasoning. But this was previously like a major hurdle for actually a lot of the transformer model. It's unable to like do the association backwards from what it has trained on. And it is shown that diffusion models are able to like overcome that. I think it's also in part is because they kind of work like in a chain of thought pattern. Because like every time it generates a part of the text, it gets to see it and regenerates that. So so they cover how they train it respectively. Where essentially they mask the token individually. Like there are different ways to approach it. So like masking the token individually. That means what they did was that they trained the laws of the various different token sets and masks respectively, compared to other tokens, because since diffusion models are no longer like running linearly, they're able to see to the left and to the right of them all at the same time. The other thing that they did was towards more like prompt completion training, where basically the prompt is frozen and masked, and then the response is trained respectively. This is very similar to like the same thing as how people train diffusion models, where either they add noise and then they just train everything from there, or they actually freeze a part of the image and then ask it to regenerate another part of the image. So like this is one classic example. Like for example, you delete the center of the image and you train the model to like regenerate that image. So that's still a prompt and response if you structure it similarly. Yeah. Then as they covered, what else did they cover? There wasn't really, other than what they observe and as I mentioned, how the inference can trade off between lead to higher performance in overall. I think the only thing else is like the math, and then they basically showed the the model's performance over the training cost, and then it shows that it showed autoregressive baseline basically transformers. It shows that it's able to like keep up in general with transformers, leading to like potential and like more research down this path respectively. So yeah, and then they shared their benchmark respectively, which as I mentioned previously, what is of interest is that, like for example, ArcC is higher than Llama, and well, MMLU is lower, which is kind of funny because it's like this. Like we saw the same issues with RWKB, for example. With RWKB having higher ArcC and GSM 8K, while having slightly lower math and MMLU, which kind of like still leads into the like one of the current hypotheses that is a different attention mechanism may favor different architectures. Yeah. Yeah, and I think that's about it. I already showed the sampling process through the animation here. So yeah. Yep. Yeah, so that's yeah. Anyone has any questions? So, matching.
I had a quick question, mostly from the chat. So since we have language diffusion now, is there any language flow matching models?
Ooh, not that I know of. Because I think this is just fresh out of the oven. So yeah, but I don't see why not down the line.
I'm a little bit, so I'm not sure here. I didn't read, I still haven't read this paper, but we actually covered this a little bit previously too. So, I mean, this is really similar to BERT, right? And it feels to me like we're basically just training it to like an encoder only model, but just with multiple steps. And it's unclear to me, the flow matching models require the Gaussian assumption, and I don't know that Gaussian assumption is here or not. So yeah, like I haven't read the paper though, so.
Gaussian function. Let's just do a quick check for that.
The same.
From what I understand, so like the language diffusion model, right? What they said here, right, is that they use the same sampling techniques for the individual tokens as existing approach for transformers. So we're not so I don't think they're using like Gaussian sampling. They're just literally like at the individual token slots. These are the logits, and they sample from there. And I assume what's happening as well is that there's probably like either low temperature or a top P setting. Did they write top P? No, they didn't say top P. Yeah. I think one of the things that they did to make it more stable is probably either a lower temperature or top P setting, where essentially like the model will the individual tokens will eventually represent their 90 plus percentile representation. And the idea is that once you put the output back into the input for the diffusion, if it's confident in that same input token, it will with high probability output the same token, and everything will then eventually stabilize. So it's not diffusion. It's really it's really just yeah, it's just sampling. It's standard sampling. That's what they say. I see the question. One question I hope you answer at some point in the talk is what is left to prove with regards to pursuing others building you to use RWK as a base instead of attention. I think right now one of the biggest proof point that is not 100% absolutely proven is million token context length. Even though and above, and I feel like this is a sliding goalpost problem. So like RWKV right now is with the latest V7 paper, we are able to hit 32K context length, perfect memory, with needle in the haystack, and that's for a 3B model. The converted models are trained at 4K, so they do not survive a 32K needle in the haystack. To do a 32K needle in a haystack, we needed way more VRAM to do the conversion and training process. And so that would have required at least 4 nodes of MI300s to do 64K and 32K training and above. And you can imagine the numbers just get more ridiculous if you want to do 1 million token length. Yeah, so that is what's left to prove. But what we point to as a hypothesis in the RWK V7 paper is that we've shown that 1.5B is slightly below 32K needle in haystack, and we showed that at 3B it's more than 32K. And so we show that with increased param size and increased state size, right, that the context length actually improves in terms of the model's ability to memorize it. And therefore, right, the hypothesis is that as we scale to 72B, right, when fully trained, it should be able to handle much larger context length. Like I say, this is a hypothesis. We have not trained a 512K context length model because we do not run a cluster, a supercluster. That being said, we are training a larger context length model for Quirky 2. We already have an iteration on the existing model, which then we are using like a few things that if you look at our previous paper like Goldfinch, compressed KV caches and stuff like that, we are able to reduce the amount of memory requirement for longer context length together with RWKV. So it's a hybrid model. And we are probably going to try push this to train to 64K to and 128 and then 256K and above. So that would bring it into the category that is very well usable for most use case. So activity is what is distilled into the target model. Yes, that is for stage 1 and 2. Eventually, at the later stages, it will be distillation from logits. So that part is extremely important. A lot of previous papers, they distill from the logits, and that didn't train the attention mechanism well enough to be stabilized. What you want to do is to train as fast as possible with as little tokens as possible, all the layers, right, to mimic the original attention layers capability. And so that's why we distill between layers, because then during the backpropagation process, right, it doesn't need to guess, hey, if I backprop all these inputs and outputs, right, which layers do I need to update? There is no guess within that. It's just literally which matrix multiplication block you want to update. So that part is actually important. RWKs and RN, no, it's not. Well, it's inspired by LSTM. At this point, I would say it's closer to Transformer than LSTM. We've been rewriting this since like 5 years. We're now at version 7, so a lot of things have changed. Have you done a compute equivalent problem such as duplicate context versus the original model single version of the context? This is the same thing as the state space model team have shown that, and we have tested this as well, and we have confirmed this, is that yes, if you duplicate the context twice, the model does perform better. This applies to all linear models, respectively, not just RWK state space, and I believe XLSTM as well, though I may need to verify that. Personally, I have verified it for state space model. There was a paper on this, repeat twice linear models. Crap, I can't remember the paper name. Yeah, I'll try to search up that. Okay, so we have the repeat twice paper, and the subsequently, what was the other one that I mentioned? The MLP layers being the same across different architectures. So yeah. Another thing to highlight as well, right, is that what is exciting also, for example, for the Quirky 72B, right? And I assume this will apply to state space as well if it goes through the same process, is that, well, we have similar performance to transformers at 72B scale. When running on the same GPU, we are able to get more tokens per second in aggregate than existing transformer architecture. So we are talking about like the tokens per second comparison that the 72B model is like we are able to do like batch size 60 or 70. If you run a 72B on a H100, you're only able to do, let's say, batch size 8 or 16. And to run similar batch sizes, right, you probably need to run a transformer 8B instead. And that speed up in overall token per second is actually probably the bigger impact, because at the end of the day, production really cares about how much compute and how much tokens and how much intelligence you can extract. Yeah. RJ, do you? Yeah, just read twice, closing the recall gap. Yep, that is the paper. Yep. Thank you for finding that. So I will repost this inside here for those who wants to. If someone can find that MLP paper, that would be great as well. Yeah. So this is the just read twice paper. The TLDR is if you just, where was it, the benchmarks? Okay, I just realized that this paper is actually quite hard to read at an immediate glance, but the TLDR was that linear models perform better when you just repeat the context twice. Yeah, pretty curious about after is there language flow matching? Not too sure about that. What do you think about RWA compared to Mamba? As covered previously, like we believe that like linear attention works better because like you're able to take the one of the problems that we observe in Mamba, especially in the smaller models, is that information is merged from left to right. And if you have, and part of the reason why repeating twice works is that if, let's say, you have instruction and then you have information here will end up being merged into a single state before it gets to see instruction. So Mamba merge information like in a cascading pattern, like from left to right, together to each other side by side before it generates the next token. Sometimes what happens sometimes is that the information gets lost before it reaches the instruction, and therefore it's unable to perform the task. That is the disadvantage. But I'm also going to say that disadvantage could be academical. And when I say this is the part where sometimes because I jump between both academia and practicality, right? In production, right? Theoretical academia limitations, right, are just that. If I would argue that for state space, right, if the state size is big enough and it's able to compress all this information together, and then eventually when it merge together, there's no information loss, then the disadvantage is not really a disadvantage. Well, for RWKV, if you put the information, it will not lose that information, and then it's able to decide the following information as it process through. Yeah, in both cases, apparently repeating twice kind of mitigates this issue. So yeah, and if the inference cost is worth it, yeah, then it becomes a question of more like how do we maturitize the technology as well. Yeah, sorry. Okay, I just speak through all the questions on the chat. Yeah, anyone has any other questions?
Since nobody is, I just want to dig in a little bit more on the repeat twice thing. So I'm wondering, in the gist of the question you answered, but I wanted to know if you or anyone else done a study of like, if for the compute equivalent, right? So like, because you guys built this model that has the RWKV attention mechanism in it, so that you're, sort of like, and you're saying that like kind of sort of we get the same quality out of the model. So like, let's just pretend it's exactly the same. Then can like the quality, like if you just repeat twice, like where do you land with compute? And then like just repeat your context, right? Like, are you still more compute efficient? And what happens if you repeat 3 times or whatever to get to the point of compute equivalent and look at quality there?
Actually, that's a good question. You're talking about inference time compute, right?
Exactly. Yeah.
Well, that's the only way is to try and find out.
Yeah.
Yeah, we have not tried to repeat it that many times. I think also you have to remember part of the bigger issue is that, and this applies to both state space and RWKV, even though we are more stable over longer context length, right? The prerequisite for this is that we need to train the model to support those lengthy context lengths. And right now our longest is 32 to, we do have a 128K model. So we could repeat the experiment within, let's say, the 128K window itself. I think beyond that, we definitely want to be able to like research more into a longer context. But I think it's an interesting thought exercise, like you say, like what if you don't repeat twice? I suspect you're going to get diminishing point of return at some point. Like I think even 3 or 4 might be diminishing, but it's an interesting question, I would say.
Or maybe the equivalent way to do the experiment is that if you look at, okay, you have your 72B model, and then what is the equivalent model for the same amount of compute with the original model, right? So like an 8B model or whatever it is for a certain context length, what's the quality difference like that? Right?
So
So
the-
that you,
yeah, sorry.
yeah, no, that I think that's
Yeah, the equivalent in terms of tokens per second output, right? The equivalent would be a 32B or a 8B model, somewhere in between that range. The number changes according to context length, but that's the approximate equivalent. If you control by tokens per second, the thing is that if you have a 72B RWKV model, you still need 72 gigs, assuming floating point 8, right, of VRAM to load the model. So your minimum hardware requirement doesn't actually go down. It just means that in the same GPU, you can handle more tokens. Yeah.
okay. Yeah.
And likewise, I would say that I don't see why this is any different from Mamba, because we both scale linearly in the same way in terms of compute cost.
Yeah.
Flo, you have any question? Because just now I thought I saw you said something. Yeah.
No, it's just talking to myself about the 72 gigabytes of VRAM still required on that last like commentary.
That being said, the latest Quen model is 32 gigs and it's looking very nice.
Yeah, I'm excited with a lot of the last releases and like being able to run that stuff at home. I've been messing with a lot of voice stuff. I haven't done as much of the language model stuff locally yet or recently, but yeah, I'm excited.
How many people run the Quen 32B on at home or on your own? Okay. Oh wait. I run Quen sometimes. I use a game. Sadly, I'm GPU very GPU poor. Okay. Yeah. So just started to okay, promising. Yeah. Like I think it's nice that like if like we now have a model that's kind of like better than last year half frontier model that you can run on your laptop. So if you just follow that trend line, look at the best model now. In 2 years' time, you're going to run that on your laptop. Yeah. Okay. Then since we went through all that, asking for like anyone wants any papers to be covered for next week, or next week. There is the AI Engineering Summit. In case anyone do not know about it. No, sorry, AI Engineering World's Fair. So
From
next
from from looking at the channels, it looks like next week someone was talking about doing because the AI Engineer World's Fair is not next week but the following week, right?
following week. Oops. Yeah. Correct.
So it looks like next week somebody was gonna do large language diffusion models, if I'm not mistaken, is what I saw on the channel. And he was talking about splitting the time. I'd be interested in maybe possibly doing a paper that talks about um image generation models and diffusion as like a lead in to what he's going to talk about. Maybe that would be interesting as a way to like split the time. I could do like maybe the first 10 or 15 minutes and let him take the rest of the time. But I am interested in Google's large language diffusion model. I haven't looked into it at all, but it seemed to be super interesting. I don't know if it's like where the benchmarks are and stuff like that, but was planning on tuning in next week for his talk. I forgot who it was, but just when I think of diffusion models off the top of my head, it's like image generation models. I've also seen lately that there's quite a few of the music generation models that are also diffusion based. So I just thought it would be like to do a nice little roundup, before he gets into um, Google stuff or language models maybe. I don't know if that makes any sense, but I thought it'd be interesting.
Okay. So basically we're going to do an image diffusion as a lead into language diffusion. Basically, tomorrow will be a diffusion. I mean, next week will be a diffusion model pipeline and promoting the AI engineering warfare. If you haven't bought your tickets to come to SF and to meet us, please do so as soon as possible before all runs out. We will so after that week we'll probably organize once again on site an in-person paper reading club for the World's Fair. Yeah. And yep, I guess Flo, you'll be there. I'll be there. RJ, will you be there? Yeah. So yeah. Yeah, do suggest papers that you want to cover, and subsequently, yeah, I'm looking forward to the in-person paper club. Where and when? The exact location I may need to figure that out with Swix or for the actual for the World's Fair, but yeah, we'll figure it out. Organized by
Maybe this is a good time too to just mention last year because there's all these after events and you need tickets to a lot of them, we ended up getting split up a lot. So I just want to put out, and we can talk about this on Discord, but I want to just put out there that let's try to like get some, some sort of consensus on what events that everybody wants to go to, and try to get tickets for them together so that we can go hang out together at these events.
Okay, sounds good. Sounds good. Yeah. If anyone wants to also like organize a specific latent space event in the area, we'll probably also be able to help with that as well. Yeah, maybe before, after, or during the event. And yeah, looking forward to see you, Sam, as well. Graph Rag. Okay.
Thanks.
Ooh, this-
Sam, if you're speaking at the GraphRag thing, do you have any like pre-reading that we can do? I'm interested in understanding, like GraphRag has been a topic that keeps coming up, and I never really glom onto. I'd be curious to hear if there's like what new is happening, and we can pre-read for that.
Well, I'm essentially, I don't know if you were at when Wasim did this paper club last year, but I'm essentially like taking what he did and sort of updating it and adding to it and stuff. So if you've watched that, then you've basically seen it. But
Yeah, I was just
yeah, we've published a couple things on. It'll be about like the specialized LLM for building graphs and the retrieval aware compression and the fusion and decoder stuff that we're doing. So yeah, this group has seen a lot of it before.
It's fine. We all need to go there. So that will be, unless the schedule changes, which it might. It's 4th of June, 11:40 a.m.
Thank you.
So make sure you all go there to support Sam, a fellow Little Space member.
who
Thank
else
you.
is talking? I think Nathan Lambert is talking too, right?
Who else?
Nathan Lambert, NATO.
You know which category?
I have no idea. I think I saw in his blog that he was going to be here and talking, but maybe he just was saying he was going to be there.
All right. Okay. Okay. And we got 10 more minutes somehow. So yeah. Is there any how would you all want the paper club to be run more with, especially with papers like and topics? Because like in particular, like what is there more area of interest in particular, or is it just do we just keep things as it is? Because like trying to figure out how to like fill in the pipeline more and to avoid the situation of like, hey, I'm going to cover my own paper unless people ask for it.
I mean, I actually personally like hearing people talk about their own papers. I'd rather hear from someone who's not like the world's, most prominent, AI expert talk about their own paper than just read somebody's paper, because I feel like I get a lot out of hearing the author's take on it. So I actually kind of like that personally.
Okay. Then what I would request is that if possible, if y'all know any interesting papers, or if you know any authors to these interesting papers, and you feel like it'll be worth inviting them, just let me know. Let me, Vivo, Eugene Yan, or even Swixno, and sometimes, and we'll be willing to do the reach out. Like I think the other time was, which paper was it that I did? The previous one was the one scaling one for Illustrator AI, the PyTia paper. For example, we got Quintin on board to help cover it. Though Quintin is probably more prominent, but it doesn't need to be prominent in any shape and form. Yeah. So we'd love to hear suggestions, especially if like you know the person personally. Yeah. Okay. I want the authors to present here. Yes, please. And if you want me to reach out to them to apply more pressure, just let me know.
I also, since no one's talking, I also feel like having a bit, I feel like so there's a discussion of having like the test of time version and then the current papers version. I actually think that, in as much as there's demand, there's definitely like several curriculums that I would be interested in. Like there's like an architecture curriculum, the agents curriculum, like all sorts of different, probably diffusion or like image model. Like there's a bunch of different ones that I feel like we could put together curriculums for that I would be interested in. I would obviously wouldn't have time to do them all, but like I think in that also helpful for pre-reading because then you already know what's next week's paper and you don't and so that one criticism I have of how we do things now is that usually the paper gets announced like a day or two before the discussion and it's hard to pre-read. So if I know a week in advance, it's a lot easier for me to like over the weekend find the time or something like that.
Okay, I do have one related question. How many people in this Discord or in this paper club come from a background without coding experience? Not with. The reason why I'm asking this is that I've been exploring, and this is not a commitment, this is something that I'm still figuring out the materials on, right? Doing an entire series about like AI architecture with the assumption that you do not know coding. And my rationale behind that is that because I do like speak highly of it, like Andrew Kapati series and Fast AI series about AI architectures and stuff. All of them kind of pretty much assume you know coding, and there are lots of people like trying to understand AI better, not necessarily to build AI architectures, but just to understand it better. And yeah, I'm just like trying to see like how many people here just doesn't know code before jumping in. Okay. Oh well, I guess most people know code. I know there's a sampling bias for this Discord, so it's like just laying out the idea. The silent majority is very silent. Okay, then I think I shall just if there's no other paper suggestion, then yeah, perhaps we should do a test of time week instead. As in like, I think what we can do is we can start doing team weeks to make it easier. So I would say let's try to do a test of time week after AI engineering conference, and then because it seems like next week we can try to turn it into a diffusion week, and then we'll just try to find papers around it that make it easier to like pre-plan the paper in advance. Yeah. Okay. Then yeah, if that's the case, do we have a second? Yeah. Okay. Yeah. Then we'll try to make sure that happens. Yeah. Then I'll just end off today's one slightly early because then if you have papers that you want to suggest, just feel free to put into the Discord. Okay. Okay. Take care, everyone. See you again next week.